Alright, this is going to be the first of several videos dealing with the chemistry and reactivity, or synthesis and reactivity of ketones and aldehydes. Okay, so here is a general structure of the functional groups that we're going to be talking about in this chapter. Aldehydes, which have hydrogen directly attached to the carbonyl group. Ketone, which has two carbons attached to the carbonyl group, and a very simple one that doesn't, I guess what would be a class by itself would be formaldehyde, okay, which has two hydrogens attached to the carbonyl group. And it's a unique compound. There's only one compound that can be that. Spelled it wrong too. All right. Okay, so if we look at the general reactivity pattern of carbonyl groups in ketones and aldehydes, and we're going to also see in most of the carboxylic acid derivatives, this is the fundamental reaction right here, where a nucleophile adds to the carbonyl group. We have a partial positive charge right here at the carbonyl carbon, and the nucleophile is attracted to that partial positive charge. The product of this is an alkyl or an alkoxide. Very seldom do we isolate this. We usually treat this with a proton source, very often water, and end up with the product that you see there. Okay, a resonance structure that we can write for a carbonyl group. This is not usually what you think of as being a good resonance structure. Is this zwitterionic resonance structure here, where we put a positive charge at carbon and a negative charge at oxygen, and now we have a carbon-oxygen single bond. If you remember the rules of resonance, this is not really a good thing to do. But this resonance structure here, even though it's not a great resonance structure, it's very important to remember. It explains a lot about the chemistry. Okay? For example, if R groups stabilize positive charges, we actually stabilize the carbonyl group. We tend to make it less reactive. All right? This resonance structure here also explains a lot about the spectral properties of aldehydes and ketones and various other carbonyl-containing compounds, okay? And most specifically, their infrared spectroscopy. If you stabilize the positive charge, you make the bond more single bond-like and easier to stretch and lower stretching frequency. We'll talk about that a little bit later. Okay. An important thing to remember here is that in most reactions that we're looking at for aldehydes and ketones, the aldehyde is more reactive than a ketone. Okay? And this has to do with a couple of reasons. For one thing, this carbon here is sterically more accessible in an aldehyde. Okay. And also, a hydrogen doesn't stabilize a positive charge as well as an alkyl group does. So therefore, the carbonyl group is less stable and more reactive. All right. Let's look at the physical properties. So ketones and aldehydes, we say, are hydrogen bond acceptors, but they're not hydrogen bond donors. They do not have any hydrogens directly attached to an oxygen or a nitrogen. Okay? But because they have lone pairs, like so, they can form strong hydrogen bonds with water. Okay? Ketones and aldehydes also have relatively strong dipole-dipole interactions. Okay? So they have a strong dipole like this, and we can, so the oxygen of one aldehyde molecule like this would be attracted to the carbonyl carbon of another aldehyde molecule just through simple electrostatics. Okay, and the dipole moment that we see here is actually a lot stronger than it is in ethers, and we'll see the effect on boiling point here. Okay, so all three of these compounds here have relatively similar molecular weights. Okay, so what we see here is that the ketone and the aldehyde and the ketone have higher boiling points than the ether, and this is due to this stronger dipole that you see in the carbonyl group. Okay, all right. What we're seeing here also is a very similar effect on water solubility. Okay, so even though they aren't hydrogen bond donors, they can serve as hydrogen bond acceptors, and the solubility of the aldehyde and the ether are fairly comparable here. The ketone's a lot more soluble, and this is, I think, because the degree of alkyl character isn't that far in any direction. So it's a lot more water soluble when it's in the middle. It doesn't really have one continually long chain to the same extent here. This has 3 carbon chain. This only has two, a 2 and a 1, and apparently that makes for greater hydrogen bonding with water. Okay, all right. Ketone aldehyde syntheses. We've had a lot of them before. The very first one was in the alkene chapter, and realized that you can take any alkene and convert it to the equivalent carbon-oxygen bonds by treating it with ozone and then reducing the ozonide with zinc or triphenylphosphine or dimethyl sulfide or something like that. Okay. As an alternative, this is a little bit safer. You can use osmium tetraoxide sodium periodate to do this transformation as well. Okay, this gives you 2 ketones. Oftentimes, one of them's smaller than the other and is discarded, and that's a common tactic in synthesis. Okay, we can also cleave a 1,2-diol with sodium with periodic acid and get the ketone this way. And basically, this latter alternative method is involved, is actually using this latter reaction. Osmium tetraoxide is making the 1,2-diol, and we're cleaving it with the periodate, and the periodate is also serving as the reoxidant for osmium so that you don't have to use a stoichiometric amount of osmium. Okay, a little later in the first half of this class, we looked at the Friedel-Crafts acylation reaction, and the reaction of a electron-rich aromatic and a acid chloride, aluminum trichloride, is a good way to make a ketone that has an aryl group. Okay, and this is mostly this reaction is pretty much restricted to things that are ortho-para directors, and you usually get more para than you do ortho. Earlier in this class, we looked at how you can oxidize primary alcohols selectively to aldehydes using pyridinium chlorochromate or the Swern oxidation, and a variety of other oxidation procedures that we never talked about in class. We can reverse this process by treating it with one of these reducing agents here. Okay, if we take a secondary alcohol, we don't have to worry so much about over-oxidation, and we can use pretty much any form of chromium-6 to convert a secondary alcohol into a ketone, and again we can take it back to what we started with by treating the ketone with sodium borohydride or lithium aluminum hydride. Okay, we looked previously and noticed that, you may remember that ketones are also reactive to Grignard reagents to produce, if you have an aldehyde as your starting material, you get a secondary alcohol. If you have a ketone as your starting material, you get a tertiary alcohol. Okay, and then we have this last reaction here, which I kind of refer to as the most forgettable reaction, perhaps in the first half of the class, but we can add water to a terminal alkyne, and this goes with very solid Markovnikov stereochemistry to produce the methyl ketone. Okay, previous reactions we've had, we looked at a lot of them before, but we'll just look at them, some more examples here. So if we treat ketones or aldehydes with organolithium reagents or Grignard reagents, we can get alcohols. We can think of these, okay, because the dipole goes this way as carbanion equivalents. Okay, so we're thinking of them as being reactive in that way. So this is a classic example of nucleophilic addition to a carbonyl group. Again, a general reactivity pattern that we looked at before. And as we mentioned previously, we can do a hydride reduction of carbonyl groups to the corresponding alcohol. So an aldehyde gives a primary alcohol, and a ketone would give a secondary alcohol. And again, even though this doesn't look like H minus, it's equivalent to H minus. Okay, so hydrogen is the more electronegative of the atoms attached here. Okay, and so there's a partial negative charge at hydrogen. So we're just looking at this as being the equivalent of adding H minus to the carbonyl group. Okay, so we're going to look at some new reactions of carbonyl groups. And this first reaction here really is not a reaction at all. It's just something that happens when you expose a ketone or aldehyde to water. Okay, so when a ketone or aldehyde reacts with water, it reversibly forms this compound called a hydrate or a 1,1-diol. Okay, the important thing to remember here is that we typically just generate this at equilibrium. If we remove the water, this is going to, in most cases, spontaneously convert back into the carbonyl group. Okay? All right, so the type of carbonyl group you have, the degree of hydration kind of reflects the relative stability of the carbonyl group. Okay, so a ketone is hydrated to only a very small extent, even when it's completely dissolved in water. And here, of course, we're maximizing the concentration of water. So this is about as far as the equilibrium could ever go. In an aldehyde, okay, for acetaldehyde, it's about 60% hydrated in aqueous solution, and formaldehyde is actually 100% hydrated in aqueous solution. This compound here, I think it's actually called formalin, and that is the hydrate of formaldehyde. There are rare cases of stable hydrates. For example, this is one is a very famous one, chloral hydrate, which is a sedative, or it's the ingredient in knockout drops. And the reason the hydrate here is stable is because, forgot the carbon. All right, so we have a partial positive at the carbonyl, and we're now loading the system with these electron withdrawing chlorines, and this is a very destabilizing interaction, okay? All right, so you want electron donating groups on your carbonyl group, not electron withdrawing groups. That's why we see chlorohydrate being a stable hydrate. Ninhydrin, a protein labeling agent, is also a stable hydrate. And here, if we look at the corresponding carbonyl compound, that would be the corresponding carbonyl compound. And what we see here is that we got a lot of partial positives. So a lot of the instability of this compound is removed by just adding water to the middle carbonyl group, and that's why we have a stable hydrate for ninhydrin. Okay, here's a question for you. Which carbonyl compound will hydrate to the greatest extent in aqueous solution? You should do this on your own first. Pause the video, do it, but I'm going to go right to the answer. Okay, so what we want to do is we want to consider what type of carbonyl group we have, and then we want to look at the electronics of the situation. So issue number one is that we have aldehyde is more likely. Aldehydes are more hydrated than ketones. So we're not going to select this one. Okay, and electron withdrawing groups destabilize C double bond O, thus we're going to see more hydrate. All right, so what do we have here? Let me just see what my animation has. Okay. All right, so this is an electron withdrawing group. This is an electron donating group. And this one doesn't really have any electron donating groups or electron withdrawing groups on it. This is the one right here, paranitrobenzaldehyde, that's going to be the most hydrated. Okay? All right, so we're going to choose this one. Again, for the facts that you see at the top, they're repeated here and they're printed more legibly. Okay, so the aldehydes are more hydrated than ketones, so we're going to deselect this one. And we're going to then look at the aldehydes, and we're going to select the one that's the least, where the carbonyl group is the least stable, and that's the one that has the electron withdrawing groups. Let's go ahead and rank them. This is the most hydrated. Okay, this would be second most. This would probably be third most. And this would be the least hydrated, if we actually wanted to rank them as far as their percent hydration goes. Okay, here I'm just going to show what we've been talking about on a energy versus reaction coordinate diagram. All right, so if we destabilize this, okay, so an electron withdrawing group is going to cause this system to become higher in energy. An electron donating group is going to cause the reactants to become lower in energy. Okay, and we're looking at delta G. Remember, delta G is related to the equilibrium constant minus RTL and KEQ. Okay, so if this rises up and becomes closer in energy to the energy of the hydrate, which is, I'm showing it as typically being an endothermic reaction because in most cases the equilibrium favors the reactants. But what we see here is that as we minimize this, the positive delta G, we get more hydrate. Okay, so that's why we see this. There's a thermodynamic reason for this. And the electron donating or electron withdrawing groups really doesn't have very much effect on the energy of the hydrate because there's no conjugation. There's no conjugated system so that you can have these electronic interactions. Okay? All right. All right, let's look at the mechanism for hydrate formation. And we have two methods for hydrate formation. Let me just say something about this. It implied that you get a hydrate spontaneously when you add water to an aldehyde or a ketone. It's not spontaneous. It's actually a very slow reaction. However, you can speed the reaction up by adding an acid or a base catalyst. That doesn't affect the position of equilibrium. It just affects the rate at which equilibrium is achieved. All right, so here is the acid catalyzed mechanism. We're protonating the carbonyl group like so, and this gives us the protonated carbonyl group. And this is more reactive to nucleophiles than is this. Okay, so even relatively poor nucleophiles, just plain old neutral water, can add to this system. This leaves us with an extra proton in our hydrate, and at equilibrium it's going to move back and forth to water. Since we typically have a lot more water molecules, we're more likely to have H3O plus than the protonated hydrate. Okay? All right, so there's the acid catalyzed mechanism. Let's look at the base catalyzed mechanism. All right, so here we're using a much stronger nucleophile, hydroxide ion. Okay, and this can add to the neutral aldehyde to produce this alkoxide here, which then just reacts with the water to make the hydrate and regenerate the base catalyst. Okay? All right, let's see. I'm going to just throw out a hypothetical. What's wrong with this? I mean, so let's say in the acid catalyzed mechanism, I want to cut out a step by adding hydroxide to the protonated aldehyde. Why can't I do that? Well, the problem here is that it's not very much of this in acidic solution. So the longer mechanism that I have up here is more appropriate. So this isn't a good mechanism here, okay? But it's something that I frequently see on exam. So remember that in acidic solution, you don't have hydroxide ion. Okay, I'm going to end this video here, and then we're going to look at some other reactions in later videos. Okay.